Okay, so it's a great pleasure to have Julie Bergner today from the University of Virginia. And yes, we are going to hear about variants of the Waldhausen S construction. So thank you very much.
All right, well, thank you very much for the invitation. It's sort of fun to be virtually traveling the world. Not as much fun as it would be to actually be doing it, but so nice to have a virtual visit here. So I'm going to, after some background and things here, I'm going to talk about two different projects. So the first project is joint work with Angelica Osorno, Victoria Ozornova, Martina Rovelli, and Claudia Scheimbauer. And then the last very much work in progress project that I'm going to talk about at the end is with Walker Stern. So I'm going to start just by recalling what the classical S-dot construction is, not in its, I suppose, most classical form due to Waldhausen for what we now call Waldhausen categories, but in the setting for exact categories, because that's the form I'm going to want to generalize. It seems like it appears I need a new pen here. Excuse me. Okay, so let's let C be an exact category. And basically the features of an exact category that I'm going to use are just going to come up as we go along. So the first main thing is that I have two distinguished kinds of morphisms. So I have admissible monomorphisms. I will write like this, and admissible epimorphisms, which I will write like this. And so the idea here is an exact category has enough information to have exact sequences, and so each of these kinds of morphisms is something that can appear in the appropriate place in an exact sequence. And so now we're going to define Sn of C to be, there's slight variations of this, but I'm going to take it to be the groupoid of diagrams of the following form. It's going to take some space. Okay, so we have, if you notice, all the horizontal arrows are given by admissible monomorphisms. The vertical arrows are all given by admissible epimorphisms. And then, well, we have these stars along the diagonal. That's just going to be the zero object in the exact category. And then the last feature is that all the squares that appear in the diagram are bicartesian. So they are both push out and pullback squares. Okay, and then, well, the groupoid is just saying, well, if we just want to consider the groupoid of such diagrams, and then you have isomorphisms. So in particular, with the squares being bicartesian, this is sort of an up to isomorphism condition. And so, we might have other things that are isomorphic. We kind of just want to stick those together. So we can either leave them as groupoids or we can take their nerves. And well, as we vary over n, we get a simplicial object. So these groupoids or their nerves assemble to a simplicial object, either a simplicial groupoid or a bisimplicial set. And this is where we get the S dot of C. And I'll just mention briefly the simplicial structure. So the face maps, the DIs, are going to remove all objects and appropriate morphisms with index I. So if we took, for example, the D0, that would mean just cutting off this top row, and then you get an Sn-1 diagram. What is more interesting, say if you took D2, and this is where instead of writing the stars, this would be an A22. So you would just remove, well, this would be like A2n. So if you wanted to take D2, you would just take this L-shaped region where all the two indices appear, and then you just replace with composite morphisms as appropriate. And then the degeneracies, they're not going to come up in this talk. That these, you just insert identity maps as appropriate. Leave that for you to figure out if you haven't seen that before. And so, okay, so this is a perfectly nice thing to do. And well, why do we do this? Well, this is a fundamental construction in algebraic K-theory, which is not the direction that I'm taking this talk today. I'm looking at the construction itself, but this is used to then take K-theory spaces, or in cases where you can, to iterate to get a K-theory spectrum and so forth. So that's why this is interesting. It's why people like this. But I want to look in the direction of let's look at this simplicial object that we get. Can we say anything about it? Does it have additional structure, sort of by virtue of being the output of an S dot construction compared to some arbitrary, simplicial space? So from now on, I am going to just implicitly be replacing these groupoids by their nerves, so they're simplicial sets. You can geometrically realize them to think about spaces if you prefer. So nothing that will not really affect too much. So can we say anything about the structure of this simplicial space? And so the first result I want to cite about this, so I'm going to cite it in the form given by Galvez-Carrillo, Kock, and Tonks. And that is that S dot of C, as we've described it, is what they call a decomposition space. This is equivalent to something called a two-Segal space, and that's what I'm going to refer to it as throughout this talk. So, okay, but that's not very meaningful unless you actually know what a decomposition space or a two-Segal space is. So let me say something about that. Well, first, let me introduce what a Segal space, or to emphasize a one Segal space. So a one Segal space is a simplicial space. So this is a functor X from delta op to simplicial sets such that the Segal maps are one Segal maps. So these go from xn to iterated pullback of, run out of space here, this should be n copies of x1 along x0, and being precise, these should really be homotopy pullbacks, that these are weak equivalences for every n at least 2. Okay, but what are these maps? What do they mean? Well, these are induced by, so I have a simplicial set that's just this bunch of one simplices glued together, n of them, and I can include that into the N Simplex delta n. So, for example, when n equals 2, I have this configuration here, and this just picks out the part of the boundary of the 2 simplex that as I've drawn it here. So this is sometimes called the spine of an N simplex. And so what this gives us is some kind of up to homotopy structure of a category. So, you know, you look at a diagram like this is saying, well, every time I have one of these, I can fill it out. Well, that's when you think in terms of nerves of categories, that's being able to put in a composite and fill in the 2 simplex. And then the other way is by restriction. But if these maps were isomorphisms, that would really be like having the strict structure of a simplicial category in simplicial sets, but well, it's a weak equivalence, so it's some sort of up to homotopy version. Okay, so now that's our crash course in 1 Segal. So what about 2 Segal? So people's first impression is often that this is going to be something higher categorical, and it's not. It's actually sort of higher dimensional in an appropriate sense. So 2 Segal spaces, so these are again going to be some kind of simplicial spaces. And now instead, certain maps, so now I'm going to have an xn mapping into some iterated pullback, but now I'm going to go up a dimension. So I'm going to have some number of copies of x2 glued together along x1. And there's, in fact, going to be n minus 1 copies there. So again, these should be weak equivalences. And here, n is going to be at least 3, but this is also going to be given by some kind of triangulation data. Now, in 1 Segal, we just had one map per dimension, and that's not going to be true anymore. So let me give an example to explain what these maps are. So when n equals 3, so we'll be looking at, we want a map from x3 to x2 copies of x2 glued together along x1. And we're going to get those from triangulations of a square. So there's 2 ways to do this, at least if we don't want to add any vertices. So we can either add in an extra edge between 0 and 2, or we can add in an extra edge from 1 to 3. And with the labelings that I've put on the vertices, each of these includes into a 3 simplex. And so if you look at this, these are in fact just the two halves of the boundary of the 3 simplex. And so just as up here, each of these maps induces, previous page, just by mapping into X, we get these maps. Well, we're going to map these diagrams into X, and we're going to get maps. Well, they're both going to look like X3 going to X2 cross X2 along X1. But, I mean, what the maps are going to depend on the structure. So this one, if you look at what's happening here, this is the pair of simplicial maps D1, D3. And then the other one will be D0, D2. Okay. And so what happens more generally is for Xn, you look at all the different triangulations by vertices of the n+1 gon, regular n+1 gon, and then that will induce these maps. And so if all of those maps in all dimensions and all triangulations are weak equivalences, that's what we call a 2-Segal space. Okay, so back to this theorem. So why should S dot have this structure? So let me illustrate it just by looking at one of these maps. So let me do it for this one here, just to give you a flavor of why this is true. So if we take something in S3 of C, so that's a diagram like this. And, well, to compare to the right-hand side, well, I'm just taking these two face maps. Let me do this in a couple of different colors. So as I talked about earlier, if we do D0, the 0th face map, I'm just gonna cut off this top row. So let me draw in purple what I get when I apply D0. And then when I apply D2, this is the more interesting one, where I remove the L-shaped region. So let me draw this in pink. And so I don't have this A02, so I skip over it. And, oh, I didn't align this very well, did I? Not being very careful here. Okay. Well, I'm just gonna, rather than start over, really unfortunate I messed this up. Okay. Highlight these ones that are in the overlap. Okay, so just imagine this shifted over. This should be sitting above that star there. Okay, so we have these two face maps, but then what this left-hand side is well, it's these two diagrams. You see the overlap is just the star to the A13 to the star. That's a copy of a N Simplex, something in S1C. But then if this map is to be a weak equivalence, well, somehow we need, at least up to equivalence, need to fill it in to this bigger diagram. Well, what's basically missing is A02 and then mapping that together. But the way we get that is, well, we look at the A12, A13, A03 and say, well, that's something I can take the pullback of. So we take the pullback, call it A02. And then, well, using universal property, we then get the map there that we want. So again, up to isomorphism, in this case, coming from an exact category, we can complete this diagram into this one. However, it is not true that S dot is one Segal in general. So one Segal, if you're looking at the map from x2 to x1 cross x1 over x0, you're looking at something like this actually is also d2, d0. That's something like this. And well, if you wanted to fill this in, so this is two one simplices glued together along a zero simplex, which is just a zero object. And the question is, well, could you fill this in? And well, in this case, you can fill it in, but not uniquely, unless for some reason all your exact sequences were split. In general, that's what this comes down to. You're trying to fill this in with a monomorphism and this with an epimorphism, and in general, there's several choices. So. And, it's also true that every one Segal space is two Segal. So this is something, so two Segal is optimal. So it's not in general one Segal, but it is two Segal. So that's the relevant structure. Okay, so that's our crash course in two Segal for exact and the structure that we get. So now let's talk about generalizing it. And so our question is, so does this work for something, this whole construction that we've done and the fact that we get something two Segal, does this work for something more general than exact categories? Okay. And well, if you remember way back at the beginning of the talk, I said, I'm not really using the full strength of an exact category. I'm only using certain features of it. And so in a theorem, which was roughly done concurrently and basically independently of the other result by Galvez-Carrillo, Kock, and Tonks, Dyckerhoff and Kapranov proved more or less the same thing, except a bit just slightly more general. So they said that S dot C is a two Segal space. Two Segal space, in fact, is their terminology for C, what they call a proto-exact category. So what's proto-exact? Well, that's basically making formal this idea that, okay, take just the structure that you need from an exact category that you need to make the S dot construction work. So what is that? Well, you need to have two kinds of morphisms. They still call them admissible monomorphisms and admissible epimorphisms. You need to have a zero object. Since we wanted to have that specified along the diagonal, and then you need to have push outs and pullbacks and squares agreeing when they're of that form. So when you have a square where the horizontals are given by monomorphisms and your verticals are given by epimorphisms, you want one of those squares to be a push out if and only if it's a pullback. And so they basically axiomatize that structure and say, okay, that's what it means to be proto-exact. It's weaker than being exact. You don't have some of the other structure, but we can still do an S dot construction. So this is where my collaborators and I came in and said, well, can we generalize this any further? And we came up with what I could argue is the most, we will justify this, we'll back this up, that the most general input, so this is due to us, is something called an augmented stable double Segal space. And I will add here, just as an aside, I mentioned that this is the Waldhausen S dot construction, and Waldhausen's original construction was for something that only had one distinguished kind of morphism. He talked about categories with cofibrations and worked from that data. So that is more general, except you don't get something too Segal. You really need sort of both of these kinds of morphisms, and you need to have the pushouts and the pullbacks, not just the pushouts. Otherwise, you only get, you could argue it's half the structure of a two Segal space. When I back here, you would get that one of these maps is a weak equivalence, but the other one need not be. So it's a little harder to say what you mean by half when you go up in the dimensions. But so we can't generalize in that direction. But
you mind a little question?
Yeah, go ahead.
Yeah, sure. So in the, I cannot spell, in the Kapranov and sorry,
Dyckerhoff, yeah.
Yeah. So do they give like an example of something which is like a proto-exact category? I mean, but is not an exact category, so something like that. Or
Yeah,
maybe in your work.
They give lots of examples. I mean, I think you can do things like finite sets here, that aren't sort of algebraic enough to be an exact category, but you can do, just injections and surjections, and something like that would work.
How about like things like pointed sets?
Well, sorry, I think you do need pointed sets in order to have a zero object. So yeah, it should be pointed. I think it should be finite pointed sets. What I actually wanted to say.
Why should they be finite? Just, I mean, I was thinking pointed sets would.
I'd have to think about whether anything went wrong there. I suppose it's all right. I'd have to think about it. I've used the example of finite pointed sets. But
Okay, thank you.
Just make your life easier, but I don't know, yeah. Okay, so, all right, so now I need to tell you what these things are. And so what is this generalization? Because it seemed like we already extracted, we extracted the necessary information. How can you generalize further? Well, the way we can generalize is that this is still assuming you have a single ambient category. So you have a single category and two sort of subcategories where you have these two flavors of morphisms. But you can step out of that and say, well, no, we have two different categories that interact in a certain way. And this leads to what's known as a double category. So the main theme is you drop the requirement that these two kinds of morphism, and I sort of already started drawing them very suggestively, one horizontally and one vertically. Okay, so we want to work instead in something called a double category, or a up to homotopy generalization thereof. But let me start here. So in a double category, you have objects, denoted by dots. You have horizontal morphisms. So these are how I'll denote, like I've been denoting the, sorry, there's something in the chat. Let me check. Yeah, I'll get there in just a second, John, actually. It actually might be that the finite pointed sets doesn't, it might actually be something we have to do more generally here. I think what I'm about to get to will answer that question. If not, let me know. Okay, so we have horizontal morphisms, and then we have some kind of vertical morphisms. And if you restrict to just either objects and horizontal morphisms or objects and vertical morphisms, you have a category in the usual sense. But then you can put them together and you have this extra data of squares, where horizontal is horizontal and vertical is vertical. And then you have certain, allowable squares, and then those also have to compose. So there's axioms and things that you have to satisfy here. If you really like fancy categorical language, this is a category internal to categories is the really formal way to say this. And so that's a way to have two flavors of morphisms that sort of are independent of each other. They have to share, they have to have common objects, but okay. But then, if we want sort of an up to homotopy version of this. And just as Segal spaces are up to homotopy categories with some extra topological or simplicial structure, we can take double Segal spaces to be our up to homotopy version of double categories. So these would be functors from delta op cross delta op to simplicial sets, and you're going to satisfy Segal conditions in both variables. And that's basically encoding that both your horizontal and your vertical are like categories up to homotopy now. Okay, so now what about the pushouts and the pullbacks? Because those notions only make sense when you're in a common ambient category. So we have a new condition that has the same flavor so that we ask for, and this is called stability. And this just says that anytime I have a span that they lived in the same category, we'd talk about taking the pullback, but it's not. Or we have in the other direction, the cospan. If I have either this data or this data, they're going to determine a square. And again, that's going to be essentially unique. Again, unique in the same, well, you can ask for it unique up to isomorphism. I mean, in this kind of world, it'll be, unique up to contractible space of choices, basically. And then the last thing is this, how do we deal with the zero object? And well, the first thing we can do is say, well, let's look for something, we call it pointed instead. So let me go back to my S dot diagrams. So we don't actually need it to be a zero object. So if you look at these objects along the diagonal, you really only need them to be initial with respect to the horizontal direction and terminal with respect to the vertical direction. They don't need to play the opposite roles in the other way. So we don't need them to be a full-on zero object in either direction. So we say we have an object, still call it star, that is initial for the horizontal category and terminal for the vertical category. And now if you're really thinking ahead on this, you might remember though that when again, with the usual S dot construction, when we take S0, we just get, by definition, we get this groupoid of zero objects. So we just get some contractible space when we go to spaces. And so if I just look at these things, this will still only give two Segal spaces with, S0, C contractible. And well, that's really going to be the example. Just I think about every example we have of interest is still going to be that way, but we can actually generalize this to a multi-object version. And so this is the augmented that I mentioned earlier. And what this does is it says that, given any object X, there exist, well, again, unique or essentially unique A that has a universal property, as some sort of initial object with respect to X, and B that behaves something like a terminal object with respect to X, with A and B in A, which is called the augmentation set. Well, in general, it can be a space. So this is very weird. It does what we want, but again, just about every natural example we have is actually pointed. But okay, this gives us a way to have a more interesting zero space in our output. Okay, and so then our main theorem is that there is an equivalence of homotopy theories. So this, in fact, takes the form of equivalence of model categories, but I don't want to go into the details of the model structures today. So, and where the left adjoint is given by S dot. So this goes from augmented stable double Segal spaces to two Segal spaces. Okay, but then you might say, well, yeah, okay, but what about the functor going in the other direction? And this is what's sometimes called a total decollage construction. We call it the path construction, following some terminology of Dyckerhoff and Kapranov. And let me just sort of tell you, what each of the things here looks like. So given a two Segal space, so So you can get that X0 is the augmentation space. X1 will then form the objects. And then X2 will give both the horizontal morphisms and the vertical morphisms, although the structure maps are different. So they don't, we get the same collections of horizontal and vertical morphisms, but the way that they interact with the objects and squares is quite different. And then X3 will give you the space of all allowable squares. Okay, I realize that's a very hand-wavy description, but it gives a sense that it is something that can be given quite explicitly. In fact, I mean, when we construct this equivalence, we actually describe the other functor first, and then say, oh well, it has this nice left adjoint that happens to agree with the S dot construction. Okay, so that's the first part. How am I doing on time? Okay. So now let me talk about this other project, which is a variant in a different direction. So throughout the talk so far, I've been generalizing, and now I'm instead perhaps going to specialize.
Can I ask something?
Yes.
No.
Sure.
Is the total decalage the left adjoint of S bullet, or is it?
No, I think it's the right adjoint.
Okay, because I mean, normally.
Unless I'm
normally you would have a right adjoint to total
That's right.
decalage, which is like like the
Am I messing this up? Let me look. I think I have this written down somewhere. I should remember. It's embarrassing, but well, let me. I can look it up again at the end.
But isn't the S bullet is some sort of Holmes from a weird delta n, so it's therefore it's a right adjoint, yeah, okay, but yeah, I don't know, because since you said total decalage, I thought would be a right adjoint.
I think that's right, but I might be remembering it. Okay.
Okay, that's fine.
I'll check at the end. Okay, so I don't want to. Otherwise, I gotta I'm on my computer here, and I want to really go check quickly. I have to unshare and go look it up. So, this was all done a while ago. That's why. Anyway. Okay, so let me talk briefly about this other project, which is specializing S dot. And what we're going to look at now is specializing this construction and what happens, and then this comparison when we look at cyclic objects. So let me recall, we have Kahn's cyclic category. So lambda, which is to do that, contains delta as a subcategory. So we have 0, well, that doesn't change. And then we have 1, so 1 in delta, we have an arrow from 0 to 1, but then we have another arrow going back in the cyclic category. And then 2, we've got 0 to 1 to 2, but then we have another arrow going back from 0 to 2. And then you have some extra morphisms that you didn't have in delta because of these extra structure that we have. And so in particular, for example, you have the representable cyclic set. When you take functors from lambda op into sets, you get cyclic sets. And if you look at the representable, so the analog of delta n, we get a lambda n. And to give you a little bit of intuition for what's going on here, this has underlying space. So geometric realization, this looks like, well, delta n cross S1. So why would this be something that we would be thinking about? So there's a theorem, this is also due to Dyckerhoff and Kapranov. And they showed that, well, they looked at a variation that are twisted, but cyclic nerves of categories are 2 Segal. Now, nerves of categories are 1 Segal, but if you take these cyclic nerves, they're not necessarily 1 Segal anymore, but they are 2 Segal. Well, what's this? So the cyclic nerve is just of a category. So in degree n, these are just functors in categories, but now we're mapping in this cyclic n rather than the linear n into C. So if you do that, you end up getting something 2 Segal.
Sorry,
Yeah.
Yeah, so 2 Segal was a property of a simplicial space, right?
Yeah, so you can either think of this as well, you can also think of it as a strict condition on simplicial sets, where the corresponding maps of simplicial sets are isomorphisms.
Yeah, but here you're saying that, I mean, a cyclic nerve is a cyclic set.
Right.
It's not a simplicial set, or so. What is this? I mean,
yeah, but you can forget the cyclic structure. You can forget the cyclic structure to think of it as a simplicial set, and then ask if it's 2 Segal. So you can think of a cyclic set as a simplicial set with this extra cyclic structure.
Oh, so okay, thank you.
Okay, so right, so yeah, so right, so maybe it can. So yeah, so 2 Segal when we get down to simplicial structure. And so that's exactly the viewpoint I'm taking. So it's helpful to have that clarified. This is exactly the point of view in our question, which is what do cyclic 2 Segal spaces, again, cyclic spaces, I'm back to functors into simplicial sets now, correspond to under this S dot or path construction. Okay. And this is what I was thinking, what I've been thinking about with Walker Stern, because so in some of his thesis work, he was actually looking at what cyclic 2 Segal spaces correspond to in a different direction. And so this was a natural thing to ask. So let me make a note here that if we have a double category, so for the moment, I'm just going to talk about double categories rather than their homotopical variants, just because it's easier. That's also what we actually have results for so far. So double categories have a flip, where you basically just take a double category and take it to double category D, we take it to D flip. And this is just given by, well, leaving the objects alone. But then you reverse the roles of the two kinds of morphisms. So your horizontal becomes vertical and your vertical becomes horizontal. And in general, this is just, this is just a functor from the category, say from the category of small double categories to itself. But you could say, well, what about when it's in equivalence? So we make the following definition: a symmetric, oops, I don't know why I'm putting that, I want to put that in parentheses, that's the whole point here. A symmetric double category is a stable, augmented, and co-augmented double category such that the flip map is an isomorphism. So it's quite strong. And then subject to some compatibility. So let me go back. So stable and augmented here mean the same things that they did before. So this is our like push out and pullback squares. Augmented is this funny generalization of being pointed. The thing that needs to be explained here, I guess, is co-augmented. And co-augmented just means that the flip of it is augmented. You can formalize it in another way if you want. And this has been tricky. We can write down what they are, but not necessarily in the nicest or most efficient way. And so that's definitely something we have been working on. But here's the result that we have so far.
I have a question.
Yeah.
What map is to be an isomorphism exactly? And what's the source and what's the target?
So, well, you're taking this functor from double categories to its, so you've got the category of small double categories to itself, and you're saying, well, compare if you take the identity versus if you take the flip map, and then there's a comparison there, and you want to know if that's an isomorphism.
Still sort of unclear.
Okay.
What's the source of the isomorphism and what's the target of the isomorphism?
It would go from D to D flip. So you have a functor from double categories to double categories. And so yeah, I guess there's something to be said here about what this isomorphism is, but it's given by just that you have map, you have D, you have. I'm not helping here, but it's not hard to sit and there's something to write down here that I'm not being clear about. But if you sit down and write down how this functor works, it's not hard to write down. Just not nice to recall on the spot. Okay, so our proposition here is that cyclic two Segal sets. So these are the discrete version. Correspond to symmetric double categories. So if you apply S dot to a symmetric double category, you get a cyclic two Segal set, and that's an equivalence of categories. And in this case, it really is an equivalence of categories. There's no homotopy theory going on here. And then the conjecture is that you can extend to cyclic to Segal spaces. And well, what should be symmetric double Segal spaces. But that's, as was in the case just for the, the previous result with my other collaborators, this is the much easier one to do. The discrete one's much easier than the homotopical one. And that's partly why we're trying to get these compatibility, try to get this description of the symmetric double categories as nice as we possibly can, because, well, we want to describe an up to homotopy version. But in fact, this whole flip business is actually, in some ways, it's nicer because you're just sort of reversing rather than in double categories, because you're just sort of swapping the two simplicial directions, which, I don't know, at least for me, that's more intuitive than what's happening double categorically. But, okay, so I will stop there.
Okay, thank you, Julie. Thank you very much for the great talk. I would like to thank you for everyone. So, are there any questions for Julie?
I was wondering about the paracyclic version as well as, I mean, you described the,
Yeah.
there's the paracyclic Waldhausen construction, right? And so I wonder if that makes sense here.
That's a good question. I have not thought about that yet. But that's definitely something we need to look at. This is right. This is very much a, very beginning stages. There's a lot to think about here that we just haven't. Walker right. is my new postdoc this year, so that's how we just started working on this last fall. But the world being what it is right now, it's hard just to even get together and talk. So.
Thank you.
Can I ask, there's two papers by Michael Weiss and Bruce Williams from 98 and 2000 about duality in Waldhausen categories, where I think they're interested in Spanny-White duality. And they also have to work quite hard to sort of figure out what kind of compatibility conditions are satisfied by that duality. So it could be sort of similar to the issues you're looking at for your flip map. Do you know about these papers?
I have not looked at those papers. Yeah. That sounds like a great idea, though.
So by Weiss and Williams from 98 and 2000.
Okay, I will write that down. So one's in 98 and one's in 2000. Is that what you said?
Yeah. The one in 98 is called Duality in Waldhausen Categories in Forum Math.
Okay. Perfect. Thank you. That sounds definitely like something I need to look into.
So one little, so you mentioned that these up to homotopy double categories. So can you say something like, are you looking at the composition, for example, up to homotopy in both directions of the double category?
Exactly.
In both directions.
Right.
Okay. So that's...
Yeah, if you restrict to either simplicial direction, you get a Segal space.
I see.
Yeah.
Okay.
What about composition of squares? There also.
I'm sorry, you cut out a little bit. Could you just repeat the question?
What about composition of squares?
Yeah.
There also.
Right. Yeah. So everything is just up to homotopy. Yeah.
About this flip map.
But again, actually, the composition of squares is actually a little bit. I mean, I don't know. Again, do you like thinking simplicity or do you like thinking double category? I mean, to me, it's like, oh, it's just a double, a bisimplicial diagram, and and how the squares work out. But yeah, everything's just sort of, because all these structure maps, the Segal maps in either direction are up to homotopy. Yeah, everything's just defined up to homotopy.
Okay. about the flip map, it is from the category of double categories to double categories, or which sends D to its flip, or is a functor
Yeah.
between D to D flip.
Again, I'm sorry, you cut out a little bit at the end.
Okay, the flip map is is it a functor from a double category to its flip, or it sends a double category to its flip?
Well, it defines a functor, an
Double
endofunctor
functor.
on the category of small double categories, where
Okay.
you take a double category and send it to its flip.
Okay. Why do we have isomorphism here? For example, can we relax it to equivalence or something? Does it still work, or we strictly need isomorphism?
It seems to be the right thing for what we want. I mean, the thing is yeah, I mean, so that would, that was something that surprised me at first too. I was like, that seems weird, but it's the thing that actually does what we want. I don't know. There's, we have this definition and initial result, but I think there's a lot that we need to understand better about what's going on here. So yeah, I think this is, like I said, this is definitely work in progress, and I think, talk to us a year from now, we're going to have a much better understanding. For right now, it's Walker might understand this better than I do at the moment, but to me, it's like, well, having the isomorphism seems to do what we want. Could we relax it to an equivalence? I'm not sure. Although in some ways that would just feel more, but in some ways that would feel more appropriate, but maybe it doesn't work. I don't know.
Yeah, that would be that relaxing to equivalence. I mean, you also need to choose the direction, vertical or horizontal, or it gets very complex in double category.
Yeah.
So
Oh,
yeah.
Okay, any other questions?
I'm gonna stop sharing just so I can see people.
Okay. Okay, well, thanks again. Just to stop the recording. Maybe there are more questions, but